Welcome to a special behind-the-scenes tour of the European Spallation Source to see some places where not many people normally go, guided by two of our top scientists. Throughout this film, key terminology will appear on the screen. If you want to know more about any of those words, you can look them up on our website at ess.eu. European Spallation Source, or ESS, is currently being built outside the city of Lund in southern Sweden. When it's finished, it will be a multidisciplinary research facility based on the world's most powerful neutron source. So what does that mean? It means that researchers from many different specialties and many different countries will come here to do their experiments. The ESS is like a giant microscope, using tiny particles called neutrons instead of visible light to look deep inside the structure of materials. Researchers, or users, will put their specially prepared samples into an instrument and use the neutrons to see where the atoms inside their sample are and what they're doing. There are three main features of the ESS. The instruments, which is where the samples go, is just one. Most of the huge machine that we're building is really there to make the neutrons, a neutral particle that you can find in the middle or the nucleus of an atom. To get the neutrons out, we need a particle accelerator, which will fire a beam of high-energy particles at a giant target. Let's take a closer look, first of all, at what will be the world's most powerful linear accelerator. That's some big kit in an underground tunnel used to make tiny particles called protons go faster and faster, or accelerate, in a straight line until they hit a target. Here's Mamad Eshraqi, one of our brilliant accelerator scientists, to tell us more.
So the ESS accelerator, when in full operation in a few years from now, will be the highest power accelerator in the whole planet. We will be accelerating lots of protons, and then these protons will shoot to the target, and over there they produce the neutrons, and with those neutrons we'll do the science that we are intended to do at ESS. Those protons, every single of those, are produced at the ion source, which is behind me. At this ion source, we take a gas of hydrogen, we inject it to a chamber, and over there we heat it with a microwave, the same type of microwave oven we have at home. When the hydrogen gas is heated up, it will be like a plasma. It will be a plasma. And then this plasma will extract it using the first stage of this component to 75,000 volts. So these protons, when they leave the ion source, they will have 1% of the speed of light. At this moment, they are diverging. The protons are not very friendly with each other. So they're diverging and getting bigger and bigger, and that's not something we want. Therefore, we put components along the accelerator to focus these beams of protons to something which we can control along the accelerator. Those two turquoise components that you see behind me, we call them solenoids. They are like lenses that focus the beam, and then this will be guided all the way 600 meters along the accelerator, and we'll have more of them along the way. When the beam reached here, we have a stream of protons that are coming all the way through. To accelerate it further, we have to use a structure like the copper structure that you see behind me, and it's called the RFQ. The RFQ you see behind me is 4.5 meters long. It takes a proton, which, if you remember, had 1% of the speed of light, and accelerate them further to 10% of the speed of light. During the process, the RFQ also focuses the beam to an even smaller size and groups these protons together. So then we have 352 million groups of protons which are coming at every second. So when we have done that stage, we can say that we have completed the first stage of acceleration, and then we can continue on to measure the properties of these protons before accelerating further, and also to prepare them for the next stage of the acceleration. So by now, we have prepared the beam of protons. They have come a long way through, or not a long way through, less than 10 meters through their life, out of 600 meters. But it was a big stage in them for their life, because they were born as protons, they were accelerated to the first stage, and now they got enough momentum to be accelerated in even more energy particle accelerators that we have coming over here. So the component that will come between here and 40 meters downstream of here, we call it the drift tube LINAC, and it will increase the energy of the protons even further to 90 million electron volt, or 40% of the speed of light. if we talk about their velocity. So what do we mean when we say 19 million electron volt? It means that if you wanted to use batteries, for example, to accelerate these protons to 90 million electron volt, or to the energy that they have, we needed 60 million 1.5 volt batteries. So to create a voltage difference between the start of the ion source and the end of the DTL to be 19 million volt, if the protons which have a charge of 1 are accelerated through this structure, reach the end, then they have acquired the equivalent of 19 million electron volt. And that's what we call it the electron volt unit. Now we have a view of a stop in the background, and that's where we connect this tunnel to the gallery, where we'll see later. The waveguides are coming here, and we are providing around 3 megawatts of power to each of these 5 DTL tanks, or drift tube tanks that we had. So we have 5 of those, and it makes 15 megawatts of power. But that's not all of that power is used to accelerate the protons, because like the copper structures that we have at home, like the cables, also our cavities would get warm, and this heat has to be removed. We use water to cool down this part of the accelerator, which is coming through these pipes that you see ahead of, above my head. This cooling has to take away about half the power that we deliver to these cavities. So around 7.5 megawatts of power that we provide to these cavities will be consumed in the form of heating, because the components we have here are called normal conducting structures. They are made of copper, as again we have seen in our daily life, and when the current goes through them, they produce a little bit of heat. But since we are using lots of current over here, then we also produce more heat than we have at home. When we go further along the accelerator, we don't have normal conducting structures anymore like we have here. We will be using superconducting structures, and we'll see more of them now. So you remember that in the last structure that we saw, we were using water to cool down the structure or to remove the heat. But if you want to cool the structures even more, to minus 271 degrees Celsius, then we cannot use water anymore. It freezes at 0. We have to use a material which doesn't freeze at all, one can say. And that material is nothing but helium. The helium is produced somewhere else on the site. Actually, it's not produced. We have the helium on site, and it's through a circle. It's like a refrigerator. The engine of the refrigerator is sitting somewhere else. And that refrigerator engine is connected to the accelerator through the pipes that you can see behind me. So the helium which is coming is at minus 271 degrees Celsius, or 2 Kelvin. When they are coming to the cavity, they cool down the cavity, and when the cavities are cooled down enough, due to their material, which are niobium, they could become superconductors, meaning that all the current that we use will be used to accelerate the protons, and nothing will be wasted in the form of heat. That increased efficiency is very useful when we have an accelerator like ESS, which is the highest power accelerator, and it makes the ESS accelerator even greener. Now we have the cavities along the accelerator, and we have to run all of them at the exact time that the beam arrives. But the temperature of the tunnel, the temperature of the site, changes during winter and summer, which means that the tunnel could expand just a little bit. But the cavities had to be precise, and these temperature changes could destroy that one. And that's not something that we look forward to. To avoid that one, we have installed something that we call a phase reference line above my head. And this is like a clock, which tells all the cavities along the accelerator when they have to operate. And if the accelerator gets warmer or cooler, then the phase reference line controls that one by being temperature controlled. So we have equipment inside to control the temperature of the phase reference line itself. And then each cavity knows exactly at which moment they have to trigger. So now, when we have reached this point of the accelerator, we have finished all the acceleration. So meaning that the protons that have arrived at this point have 2 billion electron volts of energy, or 2 GeV as we call it. And at this time, they are going at 95% of the speed of light. That's pretty fast. And at this point, we don't need any more acceleration. But as I mentioned earlier, we need the focusing all along the accelerator. And we do that one using quadruples at this stage. So we have two quadruples, or two magnetic lenses, which will focus the beam every 8 meters, or every 8.5 meters to be exact. And these components are having 4 coils. That's why we call it a quadrupole. And they run with an electric current that goes through them. So they create a magnetic field. And with that one, we can focus the beam. Every now and then in one of them, we have components to measure the beam profile or the size of the beam to see if it matches our design values or not. And if it's not, then we have to adjust these quadrupoles to bring the beam back to its original size and to reduce the possible losses to the level that we can operate the accelerator. You can notice that this part of the accelerator is covered by this fabric and this plastic cover. And it's because we want to keep them very clean, because we have components that are coming next to them. And if there is any little dust on top of them, the airflow could bring that dust to the other components.
Mamad walked down to the end of the accelerator, where ultimately the beam of particles will enter the steel vessel with the target inside. There's also a beam dump, where we steer the beam when we're still in the testing phase, or to catch any particles still in the accelerator anytime that we switch it off.
Now we have reached at the point that the beam has to decide whether it's going to the target or it's going to the beam dump. So it's not the beam who decides, actually, it's us who decide. But over here we'll have a switch dipole or a switch magnet that from the control room, we set it whether to send the beam to the tuning beam dump right in front of us, as you can see behind that metallic object at the end of this corridor, or going up this ramp towards the target, which is 4.5 meters above the level of the accelerator.
Alongside the underground accelerator tunnel is a building above ground called the Klystron Gallery. The two are connected by narrow passages called stubs. Let's go and take a look.
Now we are in the Klystron Gallery. This is where we produce the power, when we have the control equipment, when we have our computers to control the machine. And over here we'll go through some other components of the facility. Behind me you see a component that we call it Klystron. A klystron is producing the RF wave that we needed for acceleration of the protons, or for any type of acceleration, one can say. But what it is very similar to a microwave oven. We take the electricity and we convert that one to waves. The frequency is 352 megahertz, meaning that it rotates 352 million times per second. And with this klystron, we produce 3 megawatts of power, which goes, and through that blue object on the background, it goes down to the tunnel and feeds the cavities. We will have 5 of these to power the DTL cavities, and there will be 1 to power the RFQ, the first copper structure that we saw in the tunnel. But the klystrons, they need lots of power. To do that, they need something like an adapter that we use to charge our mobile phones. That adapter is just a little bit bigger, as you can see behind me on my left side. This is what we call a modulator, and what this component does, it takes the electricity from the grid, stores it in its banks, and delivers to the klystron 14 times a second. That's how frequently ESS accelerator is working. We'll be producing 14 pulses every second. So this is the view of one of the stops from the Klystron Gallery side of the story. Now we are around 4 meters above the tunnel. So if you know this tunnel, or little tunnel behind me, which we call it the stop, it goes in around 6 meters, then down around 4 meters, and inside around 4 meters. As you can see, it's very cramped over here. If I try to squeeze over here, that's not that easy. And now imagine installing those components inside that tight area. So people who were installing this, I think they were very good Lego players when they were a child, because they could think about which component to install first and which components to install last. Otherwise, somebody would have been trapped inside, or we had to reinstall all these components.
Let's leave the accelerator and the Klystron Gallery and go further downstream into the target building, where the protons will enter the target at the end of their acceleration journey. Once the beam of protons hits the target, spallation occurs from our name, European Spallation Source. So what is spallation? It's actually a mining term describing how you extract smaller parts out of a rock. In our case, it is the process of a heavy metal, such as tungsten, releasing neutrons from its atoms when bombarded with high-energy particles. The target will be housed inside this huge building, more than 125 metres long, in a gigantic cylindrical space in the centre. The ESS target itself is a rotating wheel made of tungsten bricks. One early morning in October, the target vessel arrived from Spain. The vessel will hold the target wheel itself, as well as all the components needed to extract and moderate the neutrons from the target material. It weighs 45 tonnes, it's 6 metres wide and 6 metres high, and made from steel. It came in 2 pieces that were put together before being lowered into the target area. The round hole that you see in the side of the vessel is where the protons will come in once they leave the accelerator. Inside there will be the target wheel, containing the tungsten bricks. When the protons hit the nuclei of the tungsten atoms, neutrons from those atoms will be extracted due to the massive force from the protons. The neutrons will be gathered by a large moderator that will steer as many as possible out through these windows you can see, towards the neutron guides, which then guide the beam of neutrons towards the instruments surrounding the target. Let's go to one of the instrument halls where we find Sindra Petersson Årsköld, Senior Advisor to the Science Director at ESS.
Welcome to the instrument hall at ESS. This is one of 3 instrument halls that we're building, and this one is going to house 8 different instruments for science. As you can see, it's a very large room, and we are gradually filling it up with instruments and other equipment in order to do experiments in the future. You can see that it's quite high in the ceiling, and we have a rail-based crane, the big yellow construction up under the ceiling there, that helps us carry things back and forth during construction and maintenance. Right now the crane is holding a magnet, but it will also be used in operations for moving different bits of equipment, such as cryostats and magnets, between the different instruments. The 8 instruments in this hall all require really high precision. They are high resolution instruments, which means that you get a really detailed view. You get atomic level information on the samples that you measure here. One of the instruments we have is NMX, the big white box over there. And NMX will measure protein structure or the structure of other biological samples. So it'll help us gain a better understanding of biological systems. It will help us look at the interactions between candidate drugs and drug targets to be able to develop better medications for the future. We have another instrument, or we will have another instrument in this hall called BEER, which is focused on materials for engineering sciences. So BEER is going to be very special because we'll be able to study materials for engineering during processing. So the instrument is actually going to be able to emulate what's going on in heavy industry when we generate materials and components for equipment such as bridges, railways, cars, that type of thing. That means that we can work with optimizing these processes, both for making stronger, safer, better materials, but also for making the processes more effective and more environmentally friendly. When it comes to engineering sciences, part of it is about improving the processes and the materials we already use. But there's also an exploratory initiative into finding the new materials that will make our future equipment even better. For instance, there's work on self-healing materials. Self-healing materials can make a really big difference for airplane safety. Imagine, for instance, if a bird flies into the jet engine of a plane while it's up in the air. Well, that can be a very serious condition. But if you have a material that can start to self-heal, you can actually safely land the plane in order to repair it properly. What you see behind me here is the Bifrost instrument. This is a large collaboration between Norway, Denmark, Switzerland, and France. It's an instrument that's going to help us look at materials and matter under extreme conditions. So it's specialized at looking at what happens to matter when it's exposed to very high pressures, very high temperatures. It will also help us understand magnetism, a fundamental physical phenomenon that has a lot of practical applications, not least in the IT sector. Now, what you see here is shielding blocks, a large cave of shielding that's placed around the actual instrument. When a scientist makes an experiment here at Bifrost, what they'll do is they'll go into this cave, they will place the sample in the sample holder, they'll make sure they have cryostats or furnaces in place, and then they leave the cave, go to the instrument control hutch, and start the experiment. Each white concrete shielding block behind me weighs 3,700 kilos, so it's quite a heavy structure. So now we've stepped up into the guide hall. Here we have the neutron guides. So the neutrons come from the target station way over there, and they will be guided here in neutron guides not yet installed. And then they reach the instrument. You see the back of the Bifrost cave right over there. So the guides that guide the neutrons, they will actually be resting on these piles here. So you see that this pile is in a hole, and it's actually piled all the way down to bedrock, about 8 or 10 meters down. So it's a very, very stable construction. So when we get the guides here, they will rest on the bedrock, not on the actual floor of the building. What happens in a neutron experiment is that you get all the neutrons coming in pulses over from the target station. They're guided through the neutron guides, and some things happen in the guides. We make a selection of wavelengths, for instance, so that we get the spectrum we want coming into the experiment. And then inside the cave, these neutrons are going to hit the sample at the sample positions, and they will bounce off the atoms inside the sample. And all around the sample holder, we're going to have detectors that pick them up as they come out. And from that, we can gain information about the matter in the sample.
We hope you enjoyed this behind-the-scenes look at the ESS as it is today. Don't forget, if you want to find out more, check out our website, ess.eu, where you can find aerial photos, live webcams, and lots of information about the science, technology, and all of our many partners across Europe. The facility will open to first scientists in 2023. Maybe we'll see you there one day.